Hello everyone, is the Prophet Michael David, aka Aries, and today I'm going to tell you how I made that equation that I put on that sign. Okay, first things first, for all the people that aren't super mathy, what do all the symbols mean? Well, the equation itself, which is an approximation for pi, contains pretty much all of the most famous values in mathematics, and here are the heavy hitters. Okay, almost ready to go. Just this next screenshot is what I've showed in the past called Michael's equation, which is just like the prerequisite of the sine equation. So here it is. To do this, we're going to break down the equation into two parts, the left side and the right side, or the top side and the bottom side if you're looking at the sine. So here's the left side of the equation. The second screenshot is the left side of the equation in Michael's equation, but I included both of them because they are exactly equal. And they are exactly equal to the value -1. I will explain. So to put it in real simple math terms, I found an arc sine function equivalency to pi that was based on the golden ratio. And this is it. So now I had an equation where I could turn pi into the golden ratio anytime I wanted to, but there is really only one equation that I wanted to do that with, and that's Euler's identity, and this is it. So I dropped my pi equivalency into Euler's identity, and that's how I got this. And that, of course, again, is the left-hand side of Michael's equation, which means it's equal to -1, as I said. But how is that equal to the left side of the equation in the sine? Well, let's just say that the golden ratio has a lot of interesting mathematical properties. And so I used some of those to transform that 1 over 2 times the golden ratio into what you see. And this is my algebra for it. So number one, why am I trying to do this? Well, any great mathematician really wants to make their own cool equation, so that's what I was trying to do. But number two, I was trying to veil it. I'm trying to make it more complicated. I'm trying to embarrass some mathematicians, to put it honestly. But now you're asking, well, do you know, I mean, did you do your algebra properly? And is that actually equal to the golden ratio and whatnot? And yeah, I did. I used a spreadsheet and to check my math, and this is my spreadsheet. And now you might be saying, if you looked closely, that, well, your calc is close, but your minus pi is actually non zero, which means it's not equivalent to pi. And that's only because you're doing it on a spreadsheet, or I was doing it on a spreadsheet, and because you're using the golden ratio so many times, eventually the calculations are cutting off the floating point function, or the floating point. But if you actually use the simplified version from Michael's equation and do it by hand, you can see that it is a true equivalency, and I will show you that right now. That is the golden ratio, the square root of 5 plus 1 divided by 2. Just typed it into my calculator and saved it. Times 2. Reciprocal, 1 over x. Remember, that value that we're calculating is 1 over 2 times the golden ratio. Calculator in radians, not degrees, and then you hit the second function because we're doing the arc function of this, and then you do the arc sine of that number. Multiply by 10. And finally, you subtract pi and it comes out zero. Again, in some calculators, depending on how you do it, it can cut off the floating point a bit. And you can get like a number 10 times 10 to the negative 33rd, but I can assure you it's an equivalency to pi. So that in conclusion shows how the left side of the equation just equals -1. All I did was veil and transform Euler's identity. That is the right side or bottom side of the equation, depending on how you want to think of it. And that is really the secret sauce to all of this, because those are very large numbers. And so this is how I came up with it. So then I went back to Euler's identity and I thought, like, why is it so cool in general? And to me, it's so cool because Leonhard Euler took two transcendental numbers, e and pi, and he combined them together and he got an answer that was pretty normal. The true equation is written that way, e to the power of pi I plus 1 equals 0. So it contains e, pi, I, 1, and the null set 0. But then you can take 1 to the other side and get e to the pi I equals -1. But Leonhard Euler is the only person to do that. Ramanujan kind of did it. That's a story for another day. But it's so amazing that I thought that's what I want to do. I want to combine e and pi. And so I decided to go with the ln of pi, the natural log of pi. So I play around with the calculator a lot. I mean, that's how I found my pi equivalency in the first place. But I'm always like taking the reciprocals of the decimals in Udaro over and over and looking for patterns. And when I did that with the natural log of pi, this is what it looked like. That is the natural log of pi. Then you subtract 1 to get the 0.1147, then reciprocal to get that. And then you make the 6.9 negative plus 7 because you want that decimal to be under 0.5, then take reciprocal to get that. I hope you see the pattern now. So you subtract 11 to get the 0.4 something, then reciprocal to get that. Make it negative plus 25, reciprocal to get that. And finally, you make it negative plus 5, reciprocal to get that. Did you guys see it? It actually did it twice, but two of those numbers look very, very similar. And two of them, the decimals are very similar, just the first numbers are off by 2. And so I thought, let me just make a spreadsheet and see how many numbers are like that, where they have similar decimals. So looking at that spreadsheet, and I grouped them, colored them by ones with similar decimals, and I thought, with this spreadsheet or this technique, I can make two equations, one unknown, where I can roll the top one all the way back up to an equation that is in terms of the natural log of pi, and then the bottom one up to the top color, and that will be also an equation in terms of itself, x or sometimes x minus 2 or whatever it is. And then I could solve for the natural log of pi, and then take it to the power of e, and that would be a very good value for pi. And so the blue one and the green ones at top, those are both equivalent to Michael's equation. It kicks out, it is a quadratic, it kicks out two roots. You just got to pick the right one. It's the 1 minus. And that's how I came up with Michael's equation. But the teal ones, which are 17 and 27, that was my white whale. And that is the sine equation. And I knew that that would take way, way more algebra. And the numbers would get too big to either write out very efficiently or for a spreadsheet. So I had to come up with a different technique. That being said, I did a bunch of algebra by hand. And if you want to see it all, just go and check out my Sacred Algebra video that I did a month or two ago. But I did about 10 or 15 pages of algebra, really dense stuff, just for this. But I'm only going to show you screenshots of like the last few pages where I came up with the 8 variables. And you can see the algebra. So now I have a form of an equation with 8 different very large variables, which can be put together to basically kick out 2 roots of a quadratic equation. It's just another, it's not veiled, it's just I had to break it into pieces. But this is the quadratic equation. My root is, of course, the negative square root, but that still didn't totally quite get me to the finish line because now I have a value that's very close to the natural log of pi, which is 1.1447 something something something, plus my veiled Euler's identity, which is -1, and that gives me 0.1447. So I need to add 1 to the equation somehow, and that's real easy. I just introduced a value that's 2a over 2a, which changed my quadratic root to this. And then I finally had it, you know, because I had that value, which was equal to 1.1447 something something something, plus the 2a over 2a, which is equals to 1, plus the Euler's identity, which is -1. 1 and -1 cancel out. That just leaves me with the value, which is 1.1447 something something something. E up to that power is very, very close to pi because we're dealing with very, very large numbers. But now, finally, yeah, I had to check it just to make sure that it was correct. So finally, using that big number calculator that I found online, I went through each calculation and copied it and saved it onto a text file and kept everything organized to confirm that my equations were correct and the whole thing was equal just to 1.1447 something something something, very, very close to the natural log. And here are the screenshots of my work. And so, in conclusion, that is how my sine, this equation, ultimately simplifies down to this, which is a very, very close value to pi. How close? I don't really know. I'm not going to do a whole lot of commentary because the video is already over 12 minutes, although I do think I did it quickly and efficiently. But the equation depends totally on how many decimals you take out of the square root and what values you actually use for e, how many decimal places. Eventually, use enough, you're going to saturate it. But if I had to guess how many digits of pi it is, I would say somewhere between the first 50 to the first 100, but I don't know for sure. But in that light, signing off, rule number 1, do not touch other people without their consent, aka do not hurt each other. And rule number 2, it's all about honesty. Lies are ticked down, aka try not to lie. All right, you'll have a good day. I'll talk to you later.